Hey everyone, today let's talk about the right path of LSM trees in detail. I would recommend watching my other video on the overview of LSM trees before going ahead with the current video. Link in description. So let's get started. I have broken down the video into 4 parts. At first, I'll give a brief overview of all the components involved in a typical LSM tree-based database. Next, we'll go through the entire right path in detail along with various examples. Then we'll discuss about the various error cases involved and how these are dealt with. Lastly, we'll discuss one of the important issue when dealing with distributed databases, the deletes. We have some interesting edge cases here, which we'll take a look at and understand how these are avoided in an LSM tree-based database like Cassandra. In the entirety of the video, I'll explain the concepts based on Cassandra, which is a popular LSM tree-based database. All other databases which use LSM trees also follow similar concepts. First, let's understand what are the various components involved on a high level. First off, we'll divide the entire memory that we have into two things. The first is the main memory of our system, that is the RAM, while the other is a physical memory like hard disk. As you must be aware, the main memory is a lot faster in operations than the physical memory, but the contents of the main memory are not persistent and get lost when a restart happens. So memtable is an in-memory structure which stores all the incoming writes at first. Bloom filter is also an in-memory data structure whose use I'll explain later in the video. Coming to the physical memory, we have files called systables which store all our data on disk. And each systable has an index associated with it, which is also present on the disk. We also have a component called commit log, which is used for logging to help recover from a failure and restarts. Let's deep dive into how these components are exactly used in a write path. But before that, let's take a step back and think about what we expect from a system when we write something to it. The first one is that it needs to be durable. That is, the data we wrote should not be lost even if the system fails or restarts for some reason. The second thing that we would expect and be happy with is if the write latency is very less. That is, the write needs to be fast. But the problem here is that we have our physical memory, that is the disk, which is durable, but its write latency is very less. While on the other hand, we have our main memory, which is fast, but its contents are not durable. So LSM trees use the best of both worlds by storing the incoming write in the main memory and also appending a small log at a single place in the physical memory. Now you may ask, why write to the main memory at all? Why not just write it to the disk in the small log and just get it over with? The problem is that we need the data to be in a sorted order while reading a key, since we know that searching in a sorted table is way faster than searching in a random table. But inserting every write in a sorted way on a disk takes a lot of seek time, and hence we place it in a sorted way in the main memory and just append it at last in the physical memory. This structure is nothing but the mem table, while this one is our commit log. Now let's consider an example to understand this better. Say we have a write coming for a key K1. Key K1 value V1, we write it to the mem table and also append it to the commit log K1 V1 as discussed before. While writing to the mem table, we also construct a data structure for improving the read performance. It's known as the Bloom filter. Please go through my video on Bloom filter to understand it in detail. Link in description. But to explain on a high level, a Bloom filter tells you if a key is present or not present in an SS table. And it tells this probabilistically. So if a Bloom filter says a key is present in an SS table, then it may or may not be present in the SS table. But if it says that it's not present, then it means that it is definitely not present. It will be clearer with a read example as we move forward. So when we get a write for a key K1 with value V1, we update the mem table, we update the Bloom filter, and then we append it to the commit log as well. Now say we received another write for key K2, value V2. We write it to mem table, update the Bloom filter with this key, and write it to the commit log. Now, say there was some hardware failure or some power cut and we lost all our data in our main memory. That is all our mem table and the data in our Bloom filter, all of them is lost. But we still have our commit log because it's persisted on the disk. When the node boots back up after repair, we go through the commit log and replay all of its content. That is, we start the write for the keys K1 and K2 again and write them to the mem table and update them in Bloom filter. This is how we ensure the data durability. Now say we keep receiving writes for a large number of keys. We keep appending them to the mem table and updating the Bloom filter. But after a certain amount of time, our main memory will be full and we'll no longer have any space to write it to the mem table. To avoid this, what we do is that the mem table is periodically flushed as immutable sorted string tables called SS tables. K1, K2, V2, K3, V3, K4, V4. And our mem table is cleared off. And when we flush as a table, we also create an index corresponding to it, which is basically a mapping from the key to the location of its value on the disk. So all these are basically pointers to the data locations on the disk. And all of this is done, the index creation, to improve our seek time of the disk while reading the data. Now say we have a write for the same key K1, but with a different value, K1, but with a different value, V1 dash. We have also a write for some other keys, K2, V2 dash, K5, V6, K7, V9. And also the commit log is cleared off as soon as we flush the data on the SS table because the SS table is persisted on the disk. So we'll no longer be requiring any commit log. But for the new keys, we write them to commit log as well. 2v2 dash, K5 and so on. Now, since the mem table has reached its size, we again flush it as a different SS table. K1, V1 dash, K2, V2 dash, K5, K7, V6, V9. So as you can see, we have the same key with different values in different SS tables. Now, when we issue a read for this key K1, we first go and search the mem table. This mem table has been cleared off because it was already written to the SS table. So when we issue a read for this key K1, we first go and search the mem table to see if it is present in it. And if it is present, we return the value from there, but here it's not present. So now we need to search a SS tables for the key, and if the key is present, we need to return the value back to the client. So what we do here is that we know the timestamps when these SS tables were created. Say they are T1 and T2, T2 being the most recent because this SS table was recently written. So what we do here is that we start searching from the most recently written SS table, and then we go backwards and cover all the SS tables in descending order of their creation time. So first we go to the bloom filter corresponding to the most recently written SS table, present in the SS table. Then we go to that SS table and then we check its index first. Its index gives us the place where the key and the value may are present on the disk. So we can directly go to that location, get the key, and return that value back to the client. It's guaranteed that this value will be our latest value. In this case, this is V1 dash. So this is what we return back to the user. So this covers the happy path of writes in detail, but nothing's perfect and failures are bound to happen when we are working with machines. So let's understand what are the various failure conditions that can happen here. I'll continue this in a separate video because this video sort of became lengthy. Please consider liking and subscribing in case this video helped you. Thank you.